go full screen. View. Okay, thanks for being patient. I was the one who got hit. I didn't actually do the hitting, fortunately. Okay, so we're just going to review quickly just structures in neural networks, just forward and backward propagation, just from last class. And then I'll get on to how you actually train a neural network, the actual final algorithm that you use, the stochastic gradient descent. I'll do a detailed example, and finally some advice on using neural networks if you want to use them in practice, such as multi-class classification. There's a particular way that you're supposed to initialize the weights, which we'll talk about. And then how you can compute more than one prediction using linear algebra. So before what we did was we just specified a single example. You can compute more than one prediction simultaneously using linear algebra. I'll talk about that. And then there's one thing I didn't really talk about is how many layers do you choose and how many neurons per layer do you choose. So that's something that we haven't talked about yet. We just assume that we have a neural network with a bunch of layers and a bunch of neurons, but I haven't talked about how you actually design the actual network itself. We'll talk about that. And then tips on implementing in MATLAB. Okay? Hopefully, time permitting, we're going to talk about the next topic, which is support vector machines. Support vector machines is another classification algorithm, much like neural networks. And it was used primarily in the early 90s, early 2000s, because this was the predominant algorithm that took over neural networks because it was actually a little slow to train. But now the focus has shifted back on neural networks and not so much on support vector machines anymore. So I'll give a brief talk about that and a quick support vector machine demo in MATLAB. Okay? All right. So here's just a quick review of what we talked about last week. So if you have a neural network and if you want to predict outputs, like you have a neural network and you want to be able to do classification or regression, or you want to be able to take a look at the output of a neural network and predict something, you use a process which is called forward propagation. Okay? So we talked about for a single example, so let's say you have just a single example, like an example X. Well, actually, we don't need the Y here. We just want a single example X, and we want to be able to predict what the output would be. Okay? So with forward propagation, you're given a bunch of weight matrices, so you know if you have weights for each of the layers, so you have weights for the first layer, weights for the second layer, all the way out to the output layer. You're given an example X, and then you also have to know the activation function for each neuron. So there's many different activation functions you can choose. For example, you have the sigmoid that we've talked about in logistic regression. You also have what's known as the hyperbolic tangent. It's just e to the minus z subtract e to the, actually this is plus z, sorry. This is a little misnomer here. It's e to the z subtract e to the minus z divided by e to the z plus, so it's hyperbolic tangent. You also have the perceptron, which is not really used anymore, but it's still very common. All you're doing is checking the sign of the input, and if it's positive, you output a 1, if it's negative, you output a 0. And then for regression, what you do is you use what's known as the identity. So what you're doing is that you're just computing the sum of weights into the neuron, and that's it. You don't apply any function to it. It's just the whatever you throw in, that's what you get out. So that's what you use for regression. It's what's known as the linear neuron and the identity neuron. So you have different activation functions there. And so what you do is very simple. What you do is you have an example that has, as many features as you have neurons for the input layer, and then you initialize the input layer to be that particular example you're looking at, and you also have to account for the bias as well. All right? So you initialize the input layer to be the example that you're looking at, and then you're just doing a very simple forward propagation. So what you're doing is for each of the outputs that are coming out from the previous layer, all you're doing is you're summing up all the inputs that are going in that are weighted, add the bias, and then you apply the activation function on top of that. So we derived last class that finding the inputs to every single layer in the current layer L is just a matrix vector multiplication. So you take the transpose of your weight matrix, multiply that with the outputs coming from the previous layer, and that gives you all the inputs that are coming to the current layer. And then if you want to figure out what the outputs are for the current layer, you just slap a bias, and then you apply the activation function to every single element of the inputs coming into each of the neurons individually. Okay? So you keep repeating this up until the very end, where the output layer, which is capital L, will give you what the predicted output would be, but then you get rid of the bias. You don't consider the bias. You just take a look at what the output neurons would be themselves. Okay? And then here's a review of backpropagation, and then I'll talk about the actual, content of the course. So the goal of backpropagation is to be able to calculate the gradient updates. So when you're taking a look at gradient descent, you have to figure out what the derivative is of the cost function with respect to each of the parameters that you're trying to find. In this case, the parameters that we're trying to find are all the weights for every single layer, for every single input that's going into every neuron. Okay, so the backpropagation algorithm is as follows. So you have a bunch of weight matrices that we talked about before, and then you also have an example, an example with expected output. So you have an example X with an expected output Y, and then you also have the activation function and its derivative. Okay, so a couple of classes ago, when you took the derivative of the sigmoid, we found it to be this. So all you're doing is taking the function by itself and multiplying by 1 minus itself. That's the derivative of the sigmoid. Okay? If you wanted to find the derivative of the hyperbolic tan, I'll let you figure it out yourself, but it's simply just 1 minus the function itself squared. Okay, so that's what the derivative of the hyperbolic tan would be. And then if you wanted to find the derivative of the linear itself, it's just 1, because if the activation function is z, if you differentiate it, it's just equal to 1. Okay, so that's if you wanted to do regression. Okay, so here's just review from last class. So again, you initialize the input layer to be the example that you're looking for. And then what you're going to do is you're going to perform 4 propagations. So at the very beginning, you have your input layer. You calculate all the inputs that are going into each neuron and saving all the outputs for every single node and for every single layer. You perform 4 propagation using that example. And then what you're doing now is if you want to find the gradient vector, the gradient of the error, you have to calculate what the sensitivity vectors for each neuron are. So what you're going to do first is you're going to start at the output layer, calculate what the sensitivity vector would be, and it's very simply just taking the predicted output at the output layer and subtracting with every single component of the expected output that you're looking for, which would be y. You subtract them component-wise, and then what you're doing is you have this subtracted vector, and then you multiply element-wise with the inputs that are coming into the output layer, apply the derivative of the sigmoid function, and then element-wise product them. Okay? I'll obviously do an example just to make sure that we're on track. And then you want to compute the sensitivity vectors for the other layer. So what you're doing is, starting from the second last layer, you're going to chain back and go back all the way to the first layer. So starting from the second last hidden layer all the way down to the first hidden layer, you compute the sensitivity vectors as so. So you take in the inputs that are going into every neuron, apply the derivative of the sigmoid function, and then element-wise product it with this following matrix vector multiplication. So you're going to take your weight matrix at the L+1 layer, remove the first row, and matrix vector multiply that with the sensitivity vector to give you the sensitivity vectors for the other layers. And then finally, you compute the gradient updates. So what you're doing is, for every single neuron that you have, you're calculating what the gradient update would be. So for each layer, what you're doing is you're calculating the updates or by outer product, matrix vector multiplication. So you take the outputs that are coming from the previous layer, multiply that with the sensitivity vector transpose, which will actually give you a nice weight matrix that you can use to update. Okay, so that was a nice little summary. So how do we finally train a neural network? So what we're going to do is we're going to take a look at using stochastic gradient descent, because it's actually a lot faster to get the updates going. All right, so the algorithm is as follows. So first what you need are, you need some inputs, obviously. You need training examples. Okay, so we assume that there's m of them. Okay, so they're of the form just like before, right? And then x2, y2, and then there's m of them. Okay, so you have inputs. Okay, so you have this, and then what you need to do is you have to do a bunch of initializations. Okay, so the important step is that you don't, so usually when we take a look at gradient descent, you usually set all of the weights or set all the parameters equal to 0 as the initial step. And with the neural networks, that's a really bad idea, which I'll talk about in a little bit. But what you do instead is you initialize all the weights to be very small values. And I'll talk about why you have to do that in a minute. Okay, so set weight matrices. So you have the first one and then the second one and so on to be small random values. We don't initialize from 0, and I'll talk about why in a minute. So why, we will see later. So for now, just believe me and assume that this is what we have to do. Okay? So this is the first step. The second step in the initialization is we're going to create an array of cost values. So we have to, because of stochastic gradient descent, there's iterations. What we're going to do is we're going to calculate the cost at each iteration. And then we want to make sure that the cost goes down at every iteration that you're training. Okay? So create an array of costs. I'll call this J. All right? And initialize all to 0. All to 0. Okay, that's cool. Let me go to the next page. All right. The next part that you have to do is, just like in stochastic gradient descent, what you have to do is you have to randomly shuffle your data points. So what that means is that you have to rearrange the order of the data points as you see them coming in. Okay? The reason why is because stochastic gradient descent operates one example at a time. So for each example, you're computing an update. For each example, you're computing an update. One problem with stochastic gradient descent is that if you don't look at all examples simultaneously, you may experience what's known as local minima, where the cost function is no longer convex, so you'll have like little local minima in your cost function. So if you actually do it this way, your algorithm may converge, but it may not be the optimal cost. So what randomly shuffling your data points does is that it will escape local minima. So when you choose one training example, it might converge to local minimum, but if you randomly choose another one, it might jump out of that local minimum, so that it might actually go to the ultimate cost. Okay, so that's the reason why you randomly shuffle. So the purpose, it's just something that you want to keep in mind, but you don't really need to know that for the purpose of the algorithm. The purpose is to escape local minima, since we are operating on one input at a time. On one input at a time. Okay? Okay, so here's the main algorithm. So for I equals 1, 2, all the way up to k. So what we're going to do is we're going to repeat this process k times. So repeat k times. Okay? So k, in this case, k is usually large. K is usually, between like 100 and 300 or so, but I'm not going to ask you to compute 100. I'm not, on the exam, I'll say compute 1 or 2, just to make sure that you know what you're doing. K is usually large, so between like, maybe 100 to 300 or so. But it's usually not that, not that large, okay? So these iterations are, when you take a look at certain textbooks, these iterations are what are known as epochs. So one epoch is actually one iteration of stochastic gradient descent. So these are known as epochs. Nice. These are known as epochs, all right? So what you're going to do is, at the very beginning, you're going to initialize the cost at the ith epoch to be 0, okay? And then what you're going to do now is you're going to iterate through every single example, 1, 2, all the way up to m. Okay, so one epoch means that you iterate through every single example once. That's what an epoch would be, okay? So all you have to do now is you just have to repeat the process that we talked about before. So what you're going to do is you're going to set the input layer, okay, to be the example that you're looking at, the jth training example that you're looking at, okay? And then what you're going to do is you're going to compute for propagation, and remember every single input and output into every neuron, okay? And save every x, l, and sl for L equals 1, 2, all the way up to L. Okay, so capital L is the number of layers that we have, not including the input. Okay, so compute for propagation, and then what you're going to do is you're going to, now that you've computed for propagation, you need that to compute back propagation to get the gradient updates. So compute. I'm going to shorten it to be back prop because that's also an accepted term, and save all the sensitivity vectors, okay? As well as finally the gradient updates for the output layer, then the next layer, all the way down to the last one, okay? So you've done your forward prop, you've done your back prop, and then what you finally need to do now is you need to update the weights. Okay, so for every single layer that you have, you're going to update it by doing your gradient update. So it's, okay, so this is very familiar. This is gradient descent, right? So you have your initial weights, and then you have to move them in the direction of the optimal cost, right? So you update your weights there, all right? And then finally, you want to accumulate the cost. Okay, so we're going to update this cost. Okay, so this is 1 over 2m, and then, okay, this is I. Whoopsie, let me just move this. I'm running out of room. So this, oops, sorry. Plus, and this is 1 over, okay? So this is to accommodate for the fact that your output may be a vector because there might be multiple neurons. So if you want to figure out what the distance would be, you can consider your predicted output and your expected output to be vectors. So you want to find the length or the distance between the two vectors. Okay? All right, so you accumulate the cost. And then I'm also multiplying by 1 over 2 because when you differentiate, you're getting rid of that squared. And then I'm pre-dividing by m because what happens is that if you add up everything and divide by m, it's the same thing as multiplying each sample by 1 over m and adding everything all together. So when you do that, it's the same thing as accumulating the average. All right? So when you do that, finally, final weights are stored in, so as soon as you finish everything, your updated weight matrices are done. And then what you need to notice is that the costs decrease at each epoch, but they shouldn't, they should increase or they should roughly, or maybe stay the same. But they should never increase. If they increase, then you probably need to adjust the learning rate, or you might need to do something else, which we'll talk about later, or perhaps stay the same because it's stochastic gradient descent, but it should never increase or increase significantly. Okay, so once you finally have these, what you do now is you use the weight matrices to finally compute your predicted output. So these weight matrices are custom so that you can perform predictions on your training data. So you have these weight matrices that you can finally use to predict new inputs that you haven't seen before. So we use weight matrices to predict new examples. So all you have to do is just do forward propagation on these new weightings, these new matrices to finally get what you want. Okay. So that's good. This is a pretty good algorithm. It's pretty good. But then I haven't talked about regularization yet, but it's actually a very simple adjustment to put in. Regularization is good because you don't want to overfit any data. All right, so what about regularization? Okay. So let's talk about what the cost function was before that we talked about without any regularization in. So recall the cost function for neural networks, given, you have a bunch of weight matrices. Last class I represented them as, a set capital W, and it's got a bunch of weight matrices. So the first layer, the second layer, all the way up to the last layer. Okay? So these are the parameters that we want to use to make sure that the cost is reduced as much as possible. Okay, so okay. So also we're giving them training examples as well, just like we had before. So, you have the first one, the second one, and so on. Okay. Okay, so you've got a bunch of these. Okay, so if you remember what the cost function was before, it was basically this. It was just this. So it was, you want to sum over all the examples, right? And you want to take a look at what the predicted output would be for each example. And then you want to figure out what the distance or the error is between each of the predicted outputs and the expected outputs. So that's, that's pretty good. So this here is predicted output at the output layer L, okay? And this is for example I, okay? And this is expected output for example I. Okay, so we're just summing over all those errors. So it's very similar to what you saw for the cost functions that we've seen in the past. So this is what the cost function would be without any regularization. Okay, so if you wanted to add regularization in, all you have to do is just make sure that you add in you add in the parameters that you want to find, and you just square them, right? You're adding regularization to it. So to add regularization, okay, it's just like what we saw before. So it's just like previously. Okay, so all you're doing is you're just adding squared parameters, but make sure you don't touch the bias, okay, without the bias units, right? Because the bias units actually contribute the most accuracy, so you never add any regularization to the bias units, okay? So finally, it's just this as before. So let me just copy this from here. Tablets are always nice. So you have this, okay? And then we just have to add regularization. So what we need to do is we need to sum over every layer that we have. We don't do the input layer, obviously, because that's where the input's coming from. Those never get touched. So for every layer, so not the input, we don't ever need to do that because that changes, right? And then what you do now is you do it for every single node in the, every single nodes that are inputs that are coming in. Okay, let me just pull out a diagram just to be sure that we know what we're talking about. So it was this one. Okay, this is what we had before. This is a nice little diagram. And these are all G's. Okay. So what's happening here is this is for, we're summing over every layer, so starting from this point, and then take a look that, let's see here, the notation was this, right? So I would be the node that's coming from the previous layer, and J would be the node coming to the current layer. So I would be the source node coming from the previous layer, and J would be the node coming into the current layer. So if you take a look, I don't include the bias, right? So that's where I is equal to 1, so I don't include the bias. So don't include bias. Okay? And then what's happening here in this summation, what's happening here in this summation here is that I'm summing over every single weight that I have, not including the bias. Okay, so sum over all neurons, but don't include the bias. Okay, so that's all you're doing for regularization there. So then if I wanted to find the error, it's actually quite easy. So this is just for every single example, but let's do it for one. Let's do it for one example for now. So for one example, it's not bad, because this is for stochastic gradient descent. So for one example, the error is just, one of these guys. So you have the error here, and then you also have to include regularization term. So let me just copy this. The reason why I'm looking at one example is because we have to do this for stochastic. So let's just get rid of this. Okay? So this is regularization right here. Okay, cool. All right. So now that we have this, if you recall the update, if you just look at a single neuron, so recall, the update before was something like, what was it? It was delta, sorry, what is this? Okay, this is for a single neuron. Okay, so this is without regularization. Okay, so now that we've added regularization, and sorry, this should be squared. My bad. This should be squared. Okay, and then also, because we're adding regularization in, I have to have a lambda term, right? I totally forgot about that, my bad. So here, okay, so this is, I obviously forgot, this is the regularization term. Okay, and we divide by 2 because when you differentiate with respect to the weights, the 2's will cancel with the squared. So that's why the over 2 is there customarily. So this is what it is without regularization. And then if you decide to apply regularization, so, okay, so you have this term just like before. Okay, but then what's going to happen is there's actually 2 situations. This is what it would be, and this is without the bias, because we never add regularization to the bias terms, right? So without the bias term. Okay, so this is usually, for I is equal to 0, right? Because the rows or the I in X will tell you what the input neurons will be from the previous layer. So I is equal to 0 is the bias. We don't include that. And then if you want to include the regularization for everything else, you just simply add lambda and then, okay, because when you differentiate and all that, so the derivative of this will generate this term, right? And then you also have to include this. So then when you expand the cell out, when you differentiate with respect to the weight that you want, all that's left is just that, okay? So this is for the other neurons, I guess, so for I is equal to 1. Okay. So that's how you do it individually, but I'm going to talk about how to do it using linear algebra, right? So linear algebra approach. And this is the way I would recommend. Okay. Okay, so before, right, you wanted to compute the updates that were reshaped into a matrix. So it was basically, what was it? It was x, L minus 1, and then we had, okay, so this was the update here. So this is for L is equal to 1, 2, and then not including the output layer. And then if you want to do the output layer, it's very simple. You're just doing, what is it? It was, and then, okay, so this is for the output layer. Okay. Now after. It's actually very simple. Okay. So if you want to do the output list, so what you do here is that when you take a look at the weight matrices, what's happening is that the first row includes all the weight updates for the bias term. So what you're doing is that you want to add all the regularization, but you want to skip adding the first row. So what you're doing instead is the following. So you're going to do this. Okay, and then plus. Okay, so this is what you do instead. So what's going to happen here, this is a row vector of all zeros. Okay, and then this is the weight matrix for layer L. This is before any updates. So this is what it is currently, before any updates. And removing the first row. Okay, so that's what the update would be. So this is for, all the layers except the last one. And then if you actually want to compute the last one, it's very simple. You're just taking this guy and then adding regularization on top of that. Can I just move this around? Okay, so this is plus. And then Okay, so that's what it would be. So you have this, and then you have this. Okay. All right, so I'll just do one more little topic here, then I'll do a quick example. All right? So that's what the updates will be with regularization, and I'll summarize in the end. Okay, so here's the question that we've been holding off until this point. So question, why do we randomly initialize the weights? So why don't we just set everything to 0? What's the point of randomly initializing weights? Why do we randomly initialize the weights? Yep. It's a tilde. It's just to signify that it's the weight matrix without the first row. It was the convention that I established last class. Sorry? It's a tilde. It's on your keyboard. It's a key right beside the 1 when you do shift and then that. It's a squiggly. It's called a tilde. Okay, so why do we randomly initialize the weights? Okay, so here's a very simple example. So let me just lay it out. So we usually set all the weights to 0 in the past, right? Because we didn't really know any better for, regression and classification. Okay, that's what we did in the past. We usually just set all the weights to be 0 because, the cost function was convex and all that, and so it'll eventually go. Okay? So why should we not do this for neural networks? So NN stands for neural networks because I can't, I don't want to write much. Okay, so here's a very simple example. Here's the nice diagram that I have. These are all activation functions, okay? Okay, so what I'm saying is that we should, if all the weights are 0, okay, what's going to happen? Okay, so if we set all the weights to 0, what's going to happen is that every single one of these connections are going to be 0, 0, 0, 0, whatever, okay? So when you compute an input into the neuron, what's going to happen? It's a weighted sum, right? So if I take all these inputs and I sum them up and I weight them, what's going to happen is that the input into this neuron is going to be 0, right? Because if I initialize all the weights to 0, how do you compute the input into a neuron? What you're doing is you're taking all the neurons that come from the previous layer, adding them up with all the weights for all the inputs, and you're putting them into a node in the next layer. So you're going to have 0, you're going to have input times 0 plus another input times 0 all the way, and then the sum is just going to be 0, right? Every single one of these inputs is going to be 0, right? So if for all I, J, and L, what's going to happen is that the inputs will all be 0, right? Every single input into each of these neurons is going to be 0, okay? So the inputs will all be 0. And then what's going to happen is that when you decide to calculate the sensitivities and the weight updates and all that, every single update that is produced is going to be the same because you have every single input that's coming into all the neurons to be exactly the same. So what's going to happen is that if you initialize everything to 0, every single neuron is going to behave the same way. So what's going to happen is that it's not actually going to produce anything meaningful. That actually will give you inaccuracies. Okay? So therefore, the sensitivities and updates, weight updates, are all 0. That's not good. Okay? So what's going to happen is that all neurons will do the same thing. And that's not what you want. You want each neuron to act differently, based on, what the inputs are coming in. But we'll do the same thing, right? Because every single input into the next neuron is going to be 0, and then the output will all be the same values, and then all these values will be. Then what's going to happen is that once you have these values, then all these weights are going to be 0. Then you have zeros again, and then what's going to happen is that every single input into every single node is going to be 0, and then that doesn't make any sense. You're not actually computing any nice updates. Okay, so therefore, it is important that you randomly initialize. the weights. Usually you set them to small values, but sometimes it'll change. But small values are what is accepted. Okay, so enough of that. Let's actually do an example. Okay, so here's an example finally. So let's actually do, a couple, do an actual, training step of how, of how this is actually working. So suppose we have the following neural network. Okay, so it's going to look like this. So we have two neurons. We have two input neurons. Okay, so this means that we have two features. We also have a bias as well. Okay, and then we're going to have a hidden layer with just two neurons. Also, we have a bias as well. And then we finally have just an output layer with just one neuron. Okay, so we're going to have connections to every single neuron like so, right? So all these neurons in the input layer get connected to the first one like so, and then you have the same thing for the other one. Okay. Also, remember, bias units don't take in any inputs; they only send outputs. So in this case, we have something like this. Okay. All right, that's nice. Okay. So what we have is we have 2 plus 1 input neurons. So we have 2 neurons plus the bias unit. We also have 2 plus 1 hidden layer neurons, and there's only one hidden layer. And we also have just one output neuron. Okay. Okay. The activation function that we're going to use is a sigmoid. All right. So this is 1 over 1 plus the sigmoid, and the derivative is going to matter. It's just taking the sigmoid by itself, subtracted by 1 minus. Okay. So we have this. Okay. And then what we have is we have some initial weights. So initial weights. Okay. So the input from the weights going from the input layer to the first hidden layer look like this. 0.1 minus 0.2, 0.3 minus 0.4, 0.5 minus 0.6. Okay, so what does this mean? The rows tell you which node it originates from the previous layer, and the columns tell you which layer it's going to go into. Okay, so this row denotes the source, and this denotes the target. So what is this saying? So this is saying that, so the first row is the bias. So this is saying that from the bias to the first input, first neuron, this is equal to 0.1. Okay? Actually, this entire column tells you that the weights for each of the corresponding neurons into the first one. So this is 0.3 and this is 0.5. Okay? And then this column tells you all the inputs coming from each of the neurons from the previous layer into the second one. So this one here is minus 0.2, this is minus 0.4, and this is minus 0.6. Okay? And then we have the weight matrix for the second layer. It's equal to 1, minus 2, and 3. Okay? So this is saying here that for each source node that we have, so this is the bias. Okay? Also, so this as well, this is the bias. So this is saying that we have 1, minus 2, and 3. So those are our initial, those are our initial weights. Okay. Also, I've got 2 training examples, just 2 for now. So 2 training examples. Okay. So if my first input is 0, the second input is 1, the expected output is 1. And 1, 1, and 0. So assume that these are randomly shuffled. Okay, so these are randomly shuffled. I decided to do that beforehand, so you don't have to do it yourself. So this is randomly shuffled. Okay, so what we have to do now is we have to compute one epoch or one iteration or whatever of stochastic gradient descent. So SGD stands for stochastic gradient descent. Okay, so we're going to go through one concrete example. So, and also we're given that the learning rate is going to be 5. Okay? Alrighty, so let's go ahead and do an example. Okay, so the initial cost, we initialize this to be 0. Okay, that's good. Okay, so the first example that we have, okay, we know that the first feature and the second feature are 0 and 1, and this maps to 1 to be the output. So this is x1, this is x2, and then this is y. Okay, so what we need is we need to find, there's a lot of stuff we need to find. Okay, so what you need to do is first we need to figure out what the output is from the output layer. Then we got to compute the inputs into the hidden layer, the outputs of the hidden layer, inputs into the outputs of the output, and then we need to figure out what the sensitivities are. Okay, and then we also finally need to compute the update. So these are all the things we need to find, and this is just for one iteration, but it won't be so bad. Okay. All right, so the first hidden layer. So what's going to happen is very simple. You attach a 1 for the bias, okay? And then what's going to happen is that you just take each of the, the features from the example that you have, and you just add them in. So 0 and 1. This is from before, okay? Now, if you want to compute the inputs that are going into the hidden layer, you just take the weight matrix, you transpose it, and then you multiply it by the outputs that are coming from the previous layer. So this is equal to, if you transpose the matrix, we got 0.1, 0.3, 0.5. Okay, and then you multiply this by the outputs from the previous. Okay, so this is just a very simple matrix vector multiplication. So when you do this, when you add it all up, you get 0.6 and 0.8. Makes sense because you have 0.1 and then times the 0, then 0.5, so 0.1, 0.5 is 0.6. And then you have minus, sorry, that's not a positive, it's a minus. And then you have minus 0.2 times 1, and then minus 0.6 times 1, and will give you minus 0.8. Okay. Then if you want to compute the outputs for each of these, all you have to do is prepend a 1 like we did before, and then apply the sigmoid function to every single element in the input. Okay? So what you're doing is you're doing 1, and then this is g of 0.6, g of minus 0.8. You go ahead and do the sigmoid, and we get 1, 0.6457, and 0.31. Okay, so that's the output of the first hidden layer. Now we need to calculate the inputs that are going into the output. So this is W2 transpose, and then x of 1. Okay, so all you're doing is you're transposing this. This becomes a row vector now. So this is 1, minus 2, 3, and this is 1, 0.6457, 0.31, and then when you calculate this, you get 0.6388. Okay, so that's good. And then finally, x of 2, you're just applying the sigmoid, then you remove the bias, so this is g, and this is 0.6388. This is s of 2, and then we get 0.6545. Okay, so we just did forward propagation. Okay, so I figured out what the inputs are, the outputs, and then now that we have that, we got to do back propagation now. So let's compute the sensitivity for the output layer. This is simply x of L, or this is x of 2, sorry, minus y, and then element y's with, okay. Well, x of 2, this was 0.6545, okay? And the expected output, it was equal to 1. So you're going to do 0.654 minus 1, and then you want to multiply this with the derivative of s. And then if you remember, it was just g of s of 2. So this is 0.6388 times 1 minus. Okay? So this here is the derivative of the, inputs that are going in. Okay? So when you compute this, you get minus 0.0781. Okay? So that's for the output layer, and then I need to do it for the input layer now. So this is equal to g prime, s of 1, and then element y is this, with, let's see here, 2, and then, okay? So this here, this is the weight matrix without the first layer. So if you remember, the weight matrix currently, before you do any updates, was 1, minus 2, and 3. Okay? The tilde means that you remove the first row. So what's going to happen is that you just simply get rid of the first element, the first row. In this case, what's going to happen, you'll do G of, what is it? Let's see, G. Okay, so S of 1. So let me see here. S of 1 was what? It was 0.6 minus 0.8, right? So what's going to happen is that you have to apply this element y. So you have a vector here, so this is G of 0.6 times 1 minus, right? You apply the derivative to every single element individually. Okay, and then this becomes multiplied by minus 2 and 3, and then delta 2, or it was minus 0.0781. Okay, so this is really, so all you have to do is just take this and multiply with each element by itself, like that. And then when you do that, you matrix vector multiply with this. And then when you do that, you get 0.0358 and minus 0.0501. Okay, so sensitivities are done. Now all I need to do is compute the updates. Okay, so therefore, the first update is equal to x0 and then delta 1 transpose, which is equal to 101 and then 0.0358 minus 0.0501. So this is what's known as the outer product. It's very simple. All you have to do is take every single element in the column vector, just scale with the row vector here. So all you have to do is just take this value and multiply with each element here. That gives you the first row. So this becomes 0.0358 minus 0.0501. Okay, that's the first row. And then the second row, you take this and then you multiply with each element. In this case, this is just 0 and 0. That's the second row. And finally, you have just the same as before. Okay, and this is, okay? All right, that's the first one. And then the second one, same thing as before. So this is x of 1. Okay, so this is equal to, x of 1 was 0.6457, 0.31, and then we multiply this by 0.0781. It's just a single value. So all you're doing is you're just scaling each value here, and then we finally get minus 0.0781 and minus 0.0504 and minus 0.0242. Okay, so these are the updates. Okay, so now that you've completed the updates, what you have to do now is you have to update the actual weight matrices. Okay, so when you do that, so once I finish this up, we'll take a break. So now the update is, so this is, okay, this is 5, okay, and then, you know, when you plug everything in, so you got, the initial weight matrix was 0.1 minus 0.2, 0.3 minus 0.4, 0.5 minus 0.6, minus 5, and then we have this from before, this up here. Copy. Okay, so when you do this, the actual update becomes minus 0.0788, 0.3, 0.3212, and this is 0.0507, minus 0.4, and this is minus 0.3493. Okay, that's the first one. And the second one I'll just write down for you so you can, you know, so it's just the same process. All right, so it's basically this. I'll let you figure that out, you know, I'll let you do that on your own. So this is 1.5907 minus 1.7478 and 3.1211. Okay, and then finally you want to accumulate the cost, right? So this is J plus 1 over 2, and then there's only 2 examples. The initial cost was 0, and then we have, let's see here, it was 0.645 minus 1, okay, which is finally updated to 0.0298. Okay, so that was just for the first example. The second example, I'm just going to throw the answers on, and you can verify that for yourself. So, and then let me just throw that in. Here it is. I worked it out myself earlier. All right, I'll just put that up here. Here, so here's the second example. So when you calculate the second example, here are all the quantities. So this is the first one. Obviously, you know, the first two features are 1 and 1, and the expected output is 0. You calculate everything, so this is all forward propagation, and then what's going to happen is you do the back propagation, and then these are the weight updates. And then remember, what you're doing is you're taking the previous weights and then you're adding on top these updates, and then, you know, the cost itself updates as well. So I'll let you verify that for yourself. But you're just repeating everything that I did before, but now the weight matrices are updated. So then you just repeat everything. Okay, so we'll take a break, and then we'll come back and I'll talk about more about the neural networks when you come back.